Welcome to Lesson 6, Heat, where we will discuss the differences between heat and temperature, sources of heat, and the methods of heat transfer, as well as specific heat capacity and material expansion due to the absorption of heat. Heat can be defined as a form of energy produced only by the conversion of the other forms of energy, or the total kinetic energy of a substance. When trying to think of the difference between heat and temperature, remember that heat is the total kinetic energy of a substance, and temperature is the average kinetic energy. Heat is like the total number of points a team scores during a season, and temperature is like the average score per game. Another way to describe the difference between heat and temperature is illustrated here. If we were to take the temperature above the candle on the left, it would be the same as the temperature taken above any candle on the right. However, the group of 10 candles on the right will put out 10 times as much heat as the single candle on the left. Some forms of energy which may be converted into heat include mechanical energy via friction or the compression of gases, electrical energy such as in the heat put out by a light bulb, chemical energy such as wood or gasoline burning in a fire, radiant energy such as in X-rays, nuclear energy such as in a nuclear reactor, or energy from the sun. Nearly all heat energy here on the Earth can be directly or indirectly traced to nuclear reactions occurring in the sun. Some measurements of heat energy include the calorie, which is equal to the amount of heat required to change the temperature of 1 gram of water 1 degree centigrade, or the B.T.U, or British thermal unit, which is equal to the amount of heat required to change the temperature of 1 pound of water 1 degree Fahrenheit. 1 B.T.U equals 778 foot-pounds. The three methods of heat transfer are conduction, convection, and radiation. Conduction is the most significant means of heat transfer in a solid. On a microscopic scale, conduction occurs as hot, rapidly moving or vibrating atoms and molecules interact with neighboring atoms and molecules, transferring some of their energy or heat to these neighboring atoms. Since conduction is where heat is transferred by actual contact, solids are better conductors than liquids, and liquids are better conductors of heat than gases. Convection is usually the dominant form of heat transfer into liquids and gases. Two types of convection are commonly distinguished: free convection, in which gravity and buoyancy forces drive the fluid movement, as in the pot of boiling water pictured here, where the heat from the bottom of the pot rises to the top due to buoyancy forces; and forced convection, where a fan, stirrer, or other means is used to move the fluid, such as the forced air heating system in most homes. Heat is transferred by both conduction and convection in a reciprocating aircraft engine. Heat is transferred from the cylinder walls to the cooling fins on the exterior of the cylinder head by conduction. The heat is then wicked away via the cooling airstream by convection. Radiation is the only form of heat transfer that can occur in the absence of any form of medium. Thus, it is the only means of heat transfer through a vacuum. It is in the form of X-rays, electromagnetic waves, or radio waves. Convection and conduction transfer heat slowly. However, radiation moves at the speed of light. Radiant heat may pass through a medium without heating it, as in a greenhouse, and radiant heat travels in a straight line and may be blocked as with a shade tree. However, conduction and convection may travel in roundabout routes. Specific heat capacity is also known simply as specific heat. It is the measure of the heat energy required to increase the temperature of a unit quantity of a substance by a certain temperature interval. More heat energy is required to increase the temperature of a substance with a high specific heat capacity than one with a low specific heat capacity. The specific heat of a substance is the ratio of its specific heat capacity to the specific heat capacity of water. This table lists the specific heat capacities for some common materials. It is here only to show some examples, and there is no need to copy or memorize them. Just as do liquids and gases, solids expand when heated. Solids expand in all three dimensions when heated. To determine how much an object will expand when heated, you need to know the object's coefficient of expansion, the rise in temperature, and the length of the object. To determine how much an object will expand when heated, you can utilize this formula, where E is the amount of expansion and it equals the coefficient of expansion multiplied by the length of the object multiplied by the change in temperature. This table illustrates the coefficient of expansion for some common materials. It is here only to show some examples, and there is no need to copy or memorize them.